Okay, so in this video we're sort of starting on the second part of the geometry module. So the first part of the geometry module and the first chapter of the geometry chapters in the Cambridge textbook is around angles, similarity, volume and surface area. Okay. The second part of the geometry topic is about trigonometry, which we're just beginning on now, and the third part is about spherical geometry, which we'll get to down the track. So we're beginning on the trigonometry here, and this first video is really just a review of basic right-angled triangle trigonometry. So there's a couple of things though that we need to be aware of before we get too far into the trigonometry chapter. The first of which is to do with making sure that our CAS is in the correct angle mode. Okay, this is really important. In further maths, we will always be working with angles that are measured in degrees. And so therefore, if we're doing a problem with an angle in degrees, our CAS needs to know when we enter an angle into our CAS that that angle is in degrees. So the angle mode of our CAS must be in degrees. Now the default mode of the CAS is not degrees, it's something called radians, which is what we use exclusively in methods. So for those of you that do methods and further maths, you're going to need to be very careful about making sure that you are in the right angle mode given the situation that you are in. My advice in the past has been that in further maths, you should work in the documents area of your CAS. Okay, so creating a new document, because we need to use the documents in further maths for all the finance applications, well, not so much the finance, but certainly the data, the lists and spreadsheets and the data and statistics. We need those aspects, so we need to work in document mode in further maths. So I would suggest that you work in documents for further maths, so you can keep your settings in degrees, and that you work in the scratchpad for maths methods, where you don't need to do anything more than algebra and graphing. Okay, and that can be a nice way to keep the working separate and to allow you to sort of work with separate modes across the two things. So given that, perhaps I'll work in the document mode then. So I just need a calculator screen and I want to check. Now my degree mode these days, if you've got a relatively up-to-date CAS, shows up the top. It says deg there, so I know I'm in degree mode. If you've got a slightly older CAS and it just doesn't say deg up there, simply doing what you just saw happen, if I hover over the battery, it'll bring up a little pop-up that says what angle mode you're in. Okay. If none of that happens, you're going to need to actually, and you've got a really old operating system, I would suggest that you update your operating system. But I would click on the battery, go to document settings, and you should be able to see the angle mode here. So that's where, if you are not in degree mode, this is where you're going to need to come to change it. Okay. So I'm in degree mode, so I'm going to leave that. I'm going to cancel that. So clicking on the battery, document settings, degree. Okay, you can also do it from the home screen, but it's easier to make sure that in the current document you're in the right mode by just getting into the document and then changing it from there, in my opinion. Okay, so those instructions are there. Refer back to them when and as you need them. The second thing we're going to need is where are the trig ratios with our CAS. So there's a dedicated button for trigonometry on the CAS. Sorry, it's next to the number 7. Okay, and you've got all of the trig ratios that you're going to need. Now we don't need anything on the right half of this little panel, but we do need all the left half. Sine, cos and tan, which are short for sine, cosine and tangent, which is why we say sine, not sin. And inverse sine, inverse cos and inverse tan, which we'll review throughout this video. Okay, so once we're in the right mode, we know where to find sine, cos and tan. Let's get into solving some problems. So it's probably slightly misleading calling this defining sine, cosine and tangent, because that's something we do in maths methods. We're not in any way defining them here, but we are looking at how to use them in a right-angled triangle. So in a right-angled triangle, sine of the angle, so this, we're talking about this marked angle here, theta, is equal to the opposite side length divided by the adjacent side length. Sorry, opposite side length divided by the hypotenuse. So the side lengths are labelled relative to the angle that we're interested in. So if we're interested in this angle down here, theta, then the opposite side length is defined as the side length that is opposite that angle. Whereas the adjacent side length is the side length that is adjacent to, which is next to. That's what adjacent means, that angle. And the hypotenuse is the easiest one because the hypotenuse is always the longest side. Okay, and it will always be opposite the right angle. Okay, the right angle will always be the biggest angle in a right-angled triangle, and so therefore it will open up to give the biggest side length opposite it. Okay, so you are going nowhere in trigonometry if you can't correctly identify what is hypotenuse, what is opposite, and what is adjacent. Now, these rules that we're going to talk about here only work in right-angled triangles. So it is absolutely essential that our triangle has a right angle in it, or else we can't use these rules. We'll look at other rules we can use for non-right angled triangles. Okay, so sine of the angle is equal to the opposite side length divided by the hypotenuse. Okay. Cosine of the angle is equal to the adjacent side length divided by the hypotenuse. And tan of the angle is equal to the opposite side length divided by the adjacent side length. Okay. So an acronym we would use, looking at the first letters of each of these things, SOH, CAH, we would talk about SOHCAHTOA. These should be very, very familiar things for you from Year 9, Year 10, Year 11 General Maths. This should very much be revision. Okay, so we've got these three relationships. Each of those relationships connects two side lengths with an angle. Okay, so depending on the combination of angles and side lengths we've got, that will define whether we use sine or whether we use cosine or whether we use tangent. Okay, so that's the first thing we need to identify. Is it sine, cos, or tan in this problem? Okay, so for this particular question, example 1, we've got this 30-degree angle. That's the angle that we've been given, and so therefore that means that this side length is the opposite side length, and obviously this is opposite the right angle, and so this is the hypotenuse. So we have the opposite and the hypotenuse, and so we're going to be using sine. So we know that sine of the angle is equal to the opposite length over the hypotenuse, and so for this problem that means that sine of 30 degrees equals the opposite length, which is our unknown that we're trying to find, x, divided by the hypotenuse, which is 6. Okay, so now again, if my algebra is very poor and I'm not at all comfortable with algebra, I can solve this equation for x. Okay, I can solve sine of 30 equals x divided by 6, and I can solve that for x, and I get x equals 3. Alternatively, and what most of us will be able to do, is we'll have enough confidence to be able to rearrange this to get x on its own. So x is currently being divided by 6, so to get x on its own, we're going to need to multiply both sides by 6. So x is equal to 6 times sine 30, and then we don't need our CAS to solve anything, we can just type in 6 times sine 30 to work out what x is. Okay, so if you're confident enough with your algebra to rearrange the relationships yourself, I would, and then just type in the calculation into your CAS rather than actually solving. So x is 3 and the lengths are centimetres. Again, I've said this before, I want you to always think about, does my answer make sense? I knew that x had to be less than 6 centimetres because 6 is the hypotenuse, so nothing can be longer than that. This is also a smaller angle, so if this is 90 here and this is 30 here, that'll be 60 here. So this length is definitely longer than this length. I know it looks longer, but we don't rely on what it looks like. We rely on what we know. But given that I'm not expecting x to be a particularly long length, is what I'm getting at. So 3 centimetres it is. Okay, let's have a look at question 2. So here we've got this angle of 55, which means that 3 centimetres is the adjacent side length, and y, which is opposite the right angle, is the hypotenuse. So we've got adjacent and hypotenuse. So going back up here, adjacent and hypotenuse means we're going to use cosine. So we know that cos of theta is equal to adjacent over hypotenuse. That is cos of the angle, which in this case is 55 degrees, is equal to the adjacent side length, which is 3, over the hypotenuse, which is y. Okay, this is a slightly more complicated rearrangement. Again, if you're not comfortable, get your CAS to solve. Cos 55 equals 3 divided by y, comma y, close off the bracket, control enter, get your answer, and you're done. Okay. However, so the rearrangement's not hard, and if your algebra is okay, you'll be fine with this. So we're going to multiply both sides by y. So we get y times cos of 55 degrees. That gets rid of y out of the denominator of the fraction, which was problematic. And now to get y on its own, y is being multiplied by cos 55, and so we need to divide both sides by cos 55. So y is 3 divided by cos 55, and we want our answers to 2 decimal places where necessary. So 3 divided by cos 55, control enter, it is 5.2 decimal places, 23, and the units are centimetres. Again, that makes sense. Expected the hypotenuse to be longer than 3 centimetres. Yeah, so I'm happy with that, as it does my answer make sense. And that's where if you get something unexpected, the first thing I would think of is my CAS in the right angle mode? And then if it is, then I go back to looking at what I've done in my working out. Okay, as I said, we could always just solve straight away from this point. Menu 3.1, solving cos of 55 degrees equals 3 divided by y, solving that for y, so comma y, and we get, sorry, control enter to get it as a decimal, we get the same answer. Okay, so that's finding side lengths. Finding angles is the same starting point. Work out which of these three relationships do we need. What information do we have and what are we trying to find? So do we need to use sine, cosine or tangent? And then we need to focus on solving that equation once we've put the information into it. Okay, so if we think about the equation sine of x equals 0.5, if we're trying to solve this equation, we're attempting to get x on its own. And as with any equation, this requires us to use inverse operations. So if I'm solving 2x equals 5, I know that to get x on its own, x is being multiplied by 2. I do the opposite of multiplying by 2, which is to divide by 2. I know that if we're doing x plus 2 equals 5, to get x on its own, x is being added by 2. We need to do the opposite of adding 2, which is to take away 2. Okay. If we have sine of x equals 0.5, we need to do the opposite. X is being signed, okay? That's not the right language, but that's what it means. Sine is happening to x. Okay, that's not sine times x. You don't divide by sine. Sine is a thing, an operation, like addition, subtraction, square rooting, whatever. So you can't just divide by a square root. You have to divide by a number, or do the opposite of a square root, which is to square. So we need to know what is the opposite of sine, and the opposite of sine is quite literally opposite sine. We call it inverse sine, okay? And so the opposite of sine is inverse sine, so we're going to need to inverse sine of 0.5, okay? So my CAS, trig, inverse sine is on the bottom row, inverse sine of 0.5, we find that equals 30, okay? Alright, so let's do that for these. So that was me just talking about essentially solving this up here in the description. So let's have a look at the examples given here. So if we know that cos of theta, and theta is in degrees, which means my CAS needs to be in degree mode, is equal to 0.8. And so to get theta on its own, I need to do the opposite of cos, which is to do inverse cos, and I find that theta is inverse cos of 0.8. And then I can put that into my calculator, inverse cos of 0.8, and we want 2 decimal places, inverse cos of 0.8, control enter, well, what would give me a decimal anyway? That is 36.87 degrees, okay? So if you're in degree mode, when you do inverse cos, your answer will be in degrees. If you're not in degree mode, your answer will not be in degrees. Okay, if sine of theta degrees is equal to 2/3, that means that theta is inside the sine function. We need to do the opposite of sine, which is inverse sine of 2/3. Okay, so trig button, inverse sine of 2/3, control enter to get my answer as a decimal, 41.81 degrees to 2 decimal places. Okay, so then when we're in a triangle, we've just got that one extra step before this, and that is to actually work out whether it's sine, cos, or tan equals something. Okay, so here we want to think about, this is our angle of interest, that's what we're trying to find, and we've got these two side lengths. Okay, so this is the opposite side length, and this one is the longest side, opposite the right angle, it's the hypotenuse. So we've got opposite and hypotenuse, so we need to use sine. So we know that sine of the angle is equal to opposite over hypotenuse. So in this case, sine of the angle is called theta equals the opposite length, which is 3 over 6. And yes, 3/6 will simplify, but it's not your final answer, so we don't need to really worry about that. We need to get theta on its own, that's the most important thing. And theta is currently inside a sine function, so we need to do the opposite of sine, which is inverse sine, to get it free. And so we do inverse sine to both sides, and we get that theta equals inverse sine of 3/6 or inverse sine of 1/2. So into my CAS, inverse sine of 1/2, Control Enter, and we don't need approximates, this is an exact one. Theta is 30 degrees. In question 4, here's our unknown angle that we're trying to find. We've got these two lengths, okay? This is the opposite the angle that we're interested in, and this is next to the angle. Obviously the longest side, the hypotenuse, is over there. So we've got adjacent and opposite, and so that's about tan. Tan of theta, TOA, is opposite over adjacent. So in this case, that is tan of theta equals the opposite length, which is root 10, over the adjacent length, which is 10. And so therefore theta is the opposite of tan, inverse tan, inverse tan of root 10 on 10. So my CAS, trig button, inverse tan, square root of 10, square root of 10 divided by 10. Control Enter, and we want our answer still to 2 decimal places, I think, yep. And so theta is approximately 17.55 degrees, correct to 2 decimal places. Obviously 30 degrees is exact, we don't need to write 0.00, if it's exact we can just give the exact value. Okay, so a bit of practice of SOHCAHTOA, that is trigonometry in right angled triangles, in exercise 18A.